This conference will now be recorded.
Okay, so today's lesson is actually uh, AC generator, which we are going to learn today. So we have learned already uh, what is induction and the mathematical form of induction, or I should say Faraday's law of induction. All those things we have already learned, uh, and we have learned what is flask, etc. And change in flask will give you electromagnetic induction. So that also we have learned. So today's lesson is this part. This is the last portion of this chapter. So we'll be concluding this chapter today. So electromagnetic induction. Uh, this has a great applications, like a lot of applications in our day-to-day life. In fact, without electromagnetic induction, we cannot think of our modern life. Okay, because uh, this phenomena, electromagnetic induction, actually helps us to produce electric current, basically alternating currents. And our modern society is actually depending on the current electricity or electromagnetic phenomena. Okay, so today we'll see how we can explain the working principle of AC generator or alternating generator. What is that machine and how it works? So the inventor of this AC generator is Nikola Tesla. He has developed this machine. So let us just have a look what we have. So this uh, let us see the schematic of this AC generator. Uh, Basically, we have here a coil, and that coil will be rotated inside permanent magnetic field. Or see here, we have a rectangular coil, as you can see this one, and that coil is actually connected to a rotor. This is called rotor. That means what? It can rotate, or it can be rotated by rotor. Okay, rotor. And there are, I think this thing I have already discussed once in the previous chapter maybe. So there is a slip ring. So there are two slip rings, I think, or maybe in your previous classes you might have learned. You have slip rings and carbon brushes. Okay, so which will help this rotation to continue. Okay, so you can just see this is a rectangular coil which is carrying a current, obviously. Okay, so this is uh, actually a coil through which a current will be passed, and this coil will be actually rotated. I'm sorry, here so current will not be passed in this coil, only it will be rotated. Okay, so this is rotor with which it is connected. A rotor is a machine which can rotate this coil, and you can see this coil is placed inside a strong magnetic field. So these are the pole pieces of electromagnet. So this is north pole and south pole. If I draw the magnetic field lines, something like this. Okay, these are the direction of the magnetic field lines, and hope and we are just producing uniform magnetic field B. Okay, and you look, the magnetic fields are actually parallel to the plane. So magnetic fields and this coil is actually having they are actually lying in the same plane. That means what? Your magnetic field vector is perpendicular. In this situation, at least perpendicular to the area vector. Okay, area vector of the coil. So you look, the area vector will be something like this. Okay, outward normal, that will be area vector, and your B is this. So this is 90-degree. Okay, so in this configuration, if the magnetic field lines and the coil are in the same plane, then magnetic field will be perpendicular to the area vector. So look, let us see what are these slip rings. Actually, you can see the two ends of the coil are connected to the carbon brushes. Sorry, the slip rings, and slip rings are connected to the carbon brush, which is actually uh, connected to secondary or primary coil. So here, this is two terminals again. Look, slip rings actually, they will be, slip rings are uh, when this coil is rotated, slip rings actually they are cylindrical, but there is actually if I just draw, there is a cut. Okay, there is a cut in the cylindrical slip ring. There is a cut. It is not complete. It is not like this complete cylinder. There is a cut. So when it rotates, this wire actually changes from this slip. If I say this is one slip ring, this is slip ring two. So actually it, and this, if this is A and this is C, something like that, this A and C will be alternately, when it is rotating, alternately touching this slip ring 1 and 2. Okay, that's how the polarity will be changes. Okay, and it will continue to rotate in the same direction this way. All right, these things are already there in the previous classes also. What is the main point here is that how we produce alternating current over here. So what is the role of AC generator? Producing alternating current. Alternating current. And we have already learned in the beginning of the chapter that this can be, so current can be produced from the induction process. So I'll just write the law of Faraday's law of induction. If I write that, this is d phi b by dt. So rate of change of magnetic flux will give you or induce an EMF. So we need to see now how we can change this flask, okay, with respect to time. And if I get time rate of change of flask, obviously there will be EMF induced in this, and if there is induced EMF, then obviously E by R, this is the resistance of the coil, okay, then we'll get the current. And this current, we'll be seeing that this current will be actually alternating. That means it will be uh, changing its value from some positive maximum to negative maximum, and obviously we'll get values in between also. Alternately or periodically it will change its direction as well as magnitude. So that is called alternating current. So alternating current is a current which periodically changes its direction as well as magnitude. Not only direction, it changes its magnitude also. And generally sine or cosine curve, okay, will be the best function to derive, to represent alternating signals. Okay, so with this brief introduction, let us see how it happens over here. So how alternating current generates over here. So before that, we need to produce electromagnetic EMF, electromotive force from the induction process. So if I have to produce this electromagnetic, EMF, induced EMF, then I have to have change in the flux. So look, when I had defined magnetic flux, I had told you that this is BA cos of theta. Okay, this is how I have defined. That means the flux is actually, if you have a area like this, and if your magnetic field lines are like this, so your area has a normal direction this way, and your magnetic field is this direction. So area normal and magnetic field has certain angle theta, then flux can be written as BA cos theta, which I have already written there. Okay, BA cos theta. Okay, that means when we calculate magnetic flux, you need to remember that the magnetic flux means the magnetic field line passes through the coil through the region or through the area perpendicular to the magnetic field. If you have any inclined magnetic field, you need to take a normal component such that it will be perpendicular to the area vector. Sorry, area of the uh, area of this loop. Okay, or this circular portion. Okay. All right. So we have learned already what is flux, magnetic flux, and we know this is the way to write mathematically magnetic flux. Now see, if I want to change this flux, I can do three things. This also I had already discussed. One thing is I can change the magnetic field, change B. Okay, change magnetic field. Then you can change area. Okay, or you can change the orientation or theta, the angle between the area and magnetic field. Then also flux will change. So look, this thing changing in magnetic field is very costly process, and there are many more technical difficulties maybe. So change in magnetic field is not a good idea. So what is a good idea and sustainable idea? uh, Actually there are two. I can just change the area of the loop periodically. I can change it was like this originally. I can shrink it, I can expand it. Okay, this is the way I can do, but this also may not be so much feasible. Okay, because these are actually a mechanical system, it may break sometime. So the best possible way is that you change the angle or orientation between angle between A and area vector and B, magnetic field vector. So this is what we are going to do over here, such that the magnetic flux will change. So we'll be seeing in the next slide how it is doing that. So you look here, if suppose this coil is rotated by a rotor with a constant and uniform angular speed, that is omega. Okay, suppose the rotor is rotated with angular speed omega. Then at any time time t, theta can be written as omega into t. Okay, this is a relationship between the angle between these two A and B and the angular velocity and time. Okay, or in other words, d theta by dt is equal to angular velocity. So this relationship we may understand. Okay, so then if I write the flux at any time, linked at any time, the flux linked with this coil will be B A cos of theta, which I can write in turn be a cos of omega into t. So I'll just write, let us see from Faraday's law of induction, electromagnetic induction. So what he says that this is induced EMF will be exactly equal to minus d phi by dt. Okay, actually he had given this mathematical formula, and this sign has been given by Lenz's scientist Lenz, German scientist Lenz, and that's why actually this is the complete formula for induced EMF. And see, if I just take a derivative, you look this part BA, these are independent of time because these are magnitudes. So only thing is cos of theta is dependent on time, this term, cos of omega t. Okay, because when I rotate this, theta is changing or uh, theta is changing periodically. Okay, so suppose we'll see in the next slide how it is changing. So mathematically, let us learn here. So this is actually minus BA into omega, and this is sine omega t. If you do the derivative part, okay. So a simple mathematics, okay. So I'll just remove this portion. So what is the induced EMF I get over here? Yeah, I have done one simple mistake. So sine, if you just take the derivative of sine function, so it will give a minus. Sorry, cosine function, it will give a minus, and additional minus was over here, so it will be actually positive. Okay. So induced EMF you get from here is B A omega and sine omega t. So what you see, this is induced EMF. Induced EMF. And you can see that induced EMF is actually changing with time, and it is a sine function. You look, it is proportional to the sine function. This is a sine function or a sinusoidal wave. Okay, this sine function. Okay, that means what? This means the induced EMF, what you get in this way, just by rotating this rectangular coil in a magnetic field with certain constant angular velocity omega, induced EMF what we get is actually this one, BA omega sine of omega t. And since sine omega t, it is actually time varying, and you know it changes like this. Uh, so this is okay. So it can be represented like this with omega t into this is sine function. Okay, sine omega t. Okay, so induced EMF also will change in this way. And look, the sine has the maximum value. So it has a value ranges of values plus 1 to minus 1. This is the range. Okay, that means you will have all values in between this. Okay, so this is suppose plus 1 extremum, and this way it is minus 1. This is another extremum. Okay, so the sine function, it varies. So induced EMF is varying as a sine function. So there may be sometime a question that how does like what is how does the induced EMF vary with time, and how does flux linked with this coil vary? Actually, this is cosine function. Flux linked with this coil is actually varying as cosine function, whereas your induced EMF, and you know induced EMF, so induced current will be E by R, induced EMF by resistance of the coil or the circuit you connected it to. So this R does not have any sign or any other thing, so it is a constant quantity. So you look, this current also is actually varying as sine omega t. Okay, so in sine omega t, Sine has extremum values plus 1 or minus 1. So the induced EMF or the induced current will vary in between plus 1 and minus 1. And if you know this is a sine curve, it will be varying like this. So it is actually, this is 270 degree angle between B and A, and this is actually 90-degree angle. Okay, so it has two extremum values, one at 90 when, so we get induced EMF as B A omega sine omega t, or I can write in terms of theta also. I can just convert this as sine theta, and this theta is plus 1. So this sine theta will be plus 1, sine theta, okay, sine theta is plus 1 when theta is 90-degree, and sine theta will be minus 1 when theta is 270-degree. Okay, so these are two extremum values, and other values will come in between. Okay, and this is how we get alternating current. In the next chapter we'll be learning how to represent alternating current, and how to know its various values like instantaneous values, its amplitude, or the peak values, RMS values. There are many things we'll learn in the next chapter 7. I think 7th chapter we'll be learning that. Okay, so here we can exactly understand from this rotation how the flux is actually changing, how the flux is changing to make induced EMF 0 to maximum value plus 1 and minimum value minus 1. Let us see how it is happening. So this first stage, you look, this this is called armature also sometime. This coil is called armature. This armature is perpendicular, the plane of the armature is perpendicular to the magnetic field. That means your coil is like this. Okay, so this is perpendicular to your uh, magnetic field direction. So if this is so, then, so you know, you have, as you can see from here, maybe this figure will not be that much representative. So this figure, you look here, this is, you can see, this is the one. Okay, look, flux will be maximum over here. Okay, in this position flux will be maximum, because you will get BA cos of 0 over here. Okay, flux B, here flux is maximum, but what is induced EMF? If the flux is not changing, say if this is BA alone, then flux is not changing, flux change will be 0. So this is minus d phi by dt, phi b by dt. Since this is maximum, at that condition this will be 0, induced EMF 0. So that's why this induced EMF is here. But if you would have been asked to write what is the flux over here, flux will be the maximum over here. Okay, now just go to the second stage. Is just see the Q goes left hand side, and you know, like it is rotating in this way. So in this case, you look, the magnetic field and the coil, they are in the same plane. That means if you have, suppose I'll take some other figure. So this is magnetic field, sorry, this is area of the coil, and this is magnetic field direction. They are both in plane. So in this case, you know, the magnetic field is in this way, and the area vector will be either this way or up. Okay, so in this case the angle is actually 90-degree. Okay, so in this case you can see the induced EMF will be, see, induced EMF we know this is BA omega sine of theta. Okay, and whereas phi b is cos of theta. Phi b is BA cos of theta. Obviously, one omega factor is less in this case, in case of flask. So, okay, so if the angle is 90 degree, the flask is zero, almost zero. Okay, zero or almost zero. That means it is actually always when you see the change in the flask, you have to see the previous second and now. That means you have to see t minus 1 second what was the flask and what is now. So the difference between these two flasks will be actually changing the flask. So at any point it may be zero. Suppose here it is zero, but previously there was some fill, some flask. So that's why you will get phi b even if your absolute value of phi b is zero at any point. But in this case, the flask like induced EMF will be maximum because theta is 90 degree. So in this condition, it is maximum here. Now it will slowly decrease as it goes uh, to another node. This is actually T half, that means 180 degree. 180 degree, see in this case also. So this will be actually having some value, but this induced EMF will be 0 over there. Similarly, if you go up to 270 degree, there you will find the induced EMF will be maximum but in the opposite direction. So that's why it is uh, so this is how it is changing its direction as well as magnitude. So this is the induced EMF curve with respect to time you can see here. Okay. So this is how the AC generator works in uh, our various power plants. Okay. I'll just show you or I will just discuss that. So this coil is called actually armature. These are called magnet pole of the magnets. And you know we have seen that just by rotating the armature we can produce alternating signals. So in hydrodynamic like hydroelectric generators, what is done in case of hydroelectric generator, the water is actually made to fall on this armature. This is called turbine also. So on the turbine, and turbine is actually fall on the turbine, and turbine actually is connected to this one, uh, this coil armature, and that will rotate inside a magnetic field. And when there is a change in the flask due to this rotation, there will be alternating current generated. So in case of hydroelectric generator, that is the thing. What is the scenario in case of thermal power plant, thermal generator? In that case, coal or some natural gases are burnt to to generate huge heat, and that heat will produce steam out of water, and that steam will be passed through a very thin nozzle and made onto that made it to fall on the turbine, and turbine is connected to again the armature, which will be rotated because of the rotation of the turbine. And in case of nuclear power plant, it is done same way. Just in this case, the fuel is actually uh, the nuclear waste, which are used to produce huge temperature to produce steam, and that steam again will go to turbine and then make this loop rotate. Actually, I had just a minute. I'll see whether I have it. I just thought of showing you one simple uh, demonstration video, obviously from Google. Let me see if I can do that. It will be great for all of you. No, yeah, let me see here. Yeah, I have got that. Just see how electric generators, actually these are very important to see sometimes some um, animation, etc., etc. Let us see whether you can, I don't know whether it will open. Maybe it will open. Just a minute. Here it is. Okay, so it will actually explain you the working principle or the situation in. Okay, I think I have certain difficulties to show you here. Let me see if it works. It is well. Otherwise, I'll suggest you to see some YouTube videos on this AC generator, how they work. There are many good animations. Because of lack of time, I could not make it for you. Maybe next time onwards, I'll try my own animations to show you if time permits me. Okay. So look here. I'll just mute the sound. You just see the thing visually. Oh, net is bit slow. Hmm. I'm sorry, it is actually taking a long time. I'll just ask you to kindly see from your own system. You just go and type in the YouTube. Okay, that will show you a number of videos from where you can get the perfect idea over there. So by this we just finish the chapter. Let me just take some questions if you have. I think there are Guna Selvi and Deepa. You are attending most of the classes. So are you people able to understand what we have discussed today? Do you understand today's class? How alternating current we are generating by using AC generator? How the flask is changing over here? So this is all discussed in your book. You can just read it hereafter and then see whether you can understand this. I'll just I'll just see. We can just yeah. Do you have any questions so far? Any doubt? Or otherwise, I'll take few numerical problems. Okay, on this particular chapter. Deepa, you have some questions or query?
No, sir.
Okay, then just let me take uh, uh, at least one example, numerical example on this. Oh, sorry. Okay, I have too many things opened actually in my. Okay, so So there is a problem, a numerical problem. I'll just write few informations and I'll speak in mouth, because if I write all the whole problem, it will take long time. This is some okay, so it is some competitive exam question. So in a uniform magnetic field induction B, in a uniform magnetic field induction B, a wire, a wire in the form of semicircle, okay, in the form of semicircle. That means kind of this, okay, in the form of semicircle of radius r. So the radius is r. It is rotated about the diameter of the circle with an angular velocity. So that means it is rotated, taking this as an axis of rotation. Okay, this is rotated. Okay, so you have to imagine how it is rotating. So this space actually sometime will come here like this, again it will go there like that. Okay, it is rotating like this. Okay, so in a uniform magnetic field, that semicircular uh, wire is rotated with angular velocity omega. The axis of rotation is perpendicular to the magnetic field. Axis of rotation is perpendicular to the magnetic field. That means what? So this is the axis of rotation. So I can take magnetic field in this way then, like this. So perpendicular, this is B, and this is axis of rotation. Axis is perpendicular to the magnetic field. If the total resistance of the circuit, so this is a circuit, so semicircular circuit, it has total resistance R, it is said, resistance R. Then you have to find out the mean power generated per period of rotation. So the question is mean power generated. Okay, mean power generated per period of rotation. So this is the question. Okay, so how to do that? Power means, first of all, what is power? Power means I square R, okay, or V into I, whatever it is I can. So P is equal to V into I. E means voltage drop or potential difference or voltage difference, and this is the current. So this is the thing. So if you want to know this thing, so I think I can write over here I is equal to E by induced EMF by R. So I can write I square means E square by R square. So basically I'll get E square by R. Okay, E square by R. So that means R is given already. What is E? That is what you have to find out. So we have seen in the previous case when I was rotating a loop with omega. See, there will be a change in the flask. So flask, we know we can write in this case when there is a rotation and angular velocity is given. So instead of writing cos of theta, I'll write cos of omega t. Okay. What is A? You need to know. Okay. So the radius was given small r. Okay. If this is the semicircular path, so I know the area of this. Do I know this or not? I know that. Okay. So half of the area pi r square by 2. This is the area. B is given only B. So this part is done. Only thing with this one. Okay. So what is induced EMF then? I can write minus d phi b dt. Okay, this is how I can do. Okay, so as you do the integration, sorry, the differentiation over here, what you get? So phi b is ba. So with the minus sign, see there will be cos of. Okay, let me just write here the same thing what we had done here in the previous uh, lessons. Okay, so this will give you minus of sine omega t with a omega multiplied. Okay, so what you get here is ba omega sine omega into t. All right. So look, omega is given as it is, b is given as it is, but area I have to write. What is the area? So b into area is pi small r square by 2 into omega into sine omega t. So this is my induced EMF. So what I have seen, power was this square by r. Okay, this is what we have seen. Now if you square this out, you should be getting the result. Okay, so you just e square means b square, then pi square r to the power 4 by 4 into r, and this is obviously there was on omega square, and this is sine square omega t. Now they have asked you to find out average power. Okay, I think they have asked you to find out average power. So if it is average, they have asked you to find out average power. That means, see, I'll just clean this portion a bit. So whenever we talk about rotation of any area, then the flask you have to start from the flask, and that flask is b a cos of omega t. You have to write that, and from there you just do the derivative and things like that, and then you can find out. So we have to find out actually the average power. That's what was the question, I hope. Mean power means average power. So see, in this case, we have got the power by 4r into sine square omega t. This is what we have got. So if you want to get for a time period, full period, okay, if you want to get it, so you know what you have to do. You have to take integration, integration over 1 over t full. This is 0 to t. Okay, 1 over t 0 to t into this is p dt. Okay, this is what you have to do the integration. If I do this, actually we'll learn this thing in the next section in the AC part. So this is b square pi square r to the power 4 omega square divided by 4r. This is whole time independent constant part. Okay, so only thing is this one which is changing with time, so integration will be over that. Okay, I'll just take this out, maybe all of them. B square pi square r to the power 4 omega square 4 r, and integration here 1 by t is already there, 0 to t sine square omega into dt. So if you do this integration, for any sine for sine or cosine function, if you are doing full scale integration, when you have square, you'll get the integration. You just know this trick. You have full scale integration, full cycle integration, and if it is sine square, okay, sine square some function of t, okay, suppose omega t here, into dt. So this will actually give you the upper limit, that is t by 2. So you'll get always result of that. That means if I just put here t by 2, so tt goes off. This integration you can do elaborately, but this is a trick. When you have got a cosine or sine function square of that, you have to integrate in a full cycle. It will give you the upper limit by 2. This you can remember as a trick, or otherwise you can multiply uh, 2, then 2 sine square theta. You have to just do all the way. 1 minus cos of theta is like cos of 2 theta is equal to uh, 2 sine square theta. So those things you have to do substitution. Otherwise, you can remember this trick. You can write in a minute. If it, even if it is cosine function also, cosine. So cos square omega t dt, and over a full scale integration, this also would give you t by 2. Okay. Other than this square, you have to do integration elaborately. And if you have only cos theta, cos omega t, sin omega t, that would give you, because cos square means or sin square means, look, your curve is like this, sin square omega t. Okay. But sin omega t, the curve is like this. If you take time average, this is plus 1 and this is minus 1. This would give you 0 by full cycle. So 0 by something is 0. Okay, that's why we take RMS value, or average, square of the average. Sorry, average of the or mean of the squared quantity. Okay. So anyway, as I told, it will be giving you upper limit by 2. That means t by 2. Okay. So, and it is actually true for only square part. Okay, square, not for only cos omega t, sin omega t, or higher power. It is only for square. So I can write upper limit by 2. So look, this t goes off. So finally what we get is b square pi square omega square small r to the power 4 divided by 8r. This will be the mean power generated by that uh, arrangements. Okay, that semicircular loop, upon rotating it in a uniform magnetic field with a constant uh, angular velocity. Okay. So with this we finish the chapter. Today I think I'll stop it here. In the next class we'll start with the 7th chapter, that is alternating current. Okay, alternating current will start. And I have been giving some quiz questions. Maybe you will find it in our websites. You can just take those and practice. If you have any doubt over there, you can ask in this classes. Okay, or while I'm teaching also, you can stop me anywhere if you have any doubt anytime. Okay. So that's all for today. Uh, Deepa and Selvi, I don't know whether you have this you have understood this what I discussed now, the numerical problem. Any reply from both of you? You can write in the chat box. Okay, anyway, I'll stop it here today. We'll discuss again in the next class if you have any doubt.